welcome to another QualQuest video. Today I'm going to try and do two problems really quickly, and thus conclude the easy, quote unquote, easy questions of our qual practice exams. So our first question here is that we were given this weird integral, and then we want to find a certain function y of x, which solves roughly the same equation, but now we have an a squared and x minus u's quantity squared in the denominator. So how do we solve this? The first thing for us to notice is that our integral y of u over x minus u squared plus a squared du is actually known as a convolution, where we have two functions, a and b, respective of x, and basically you define a convolution as the integral of the two products. Instead of, in the second term, we put in u minus x. And then we integrate with respect to u, so what comes out is just a function of x. So going back to our left side of the equation, our a equation is basically our mysterious y of x, and we already know our b function as 1 over x squared plus a squared. So how are we going to be able to use our hint at the beginning to solve for y? So in order to use our first hint, we're going to have to do a Fourier transform of both sides of our equation. Basically, we're using the notation as you multiply our function f of x times e to the ikx, and with respect to x, to get some function f hat of k. And that's how we're, some books define the Fourier transform a little differently, but this is the one we're using. Fortunately for us, it turns out that if we take the Fourier transform of a convolution, then it's actually the transform of each part of the convolution separately. So then you can just split them up and multiply them. So knowing that we have a convolution on the left side, we take the transform, or the Fourier transform of our original equation. So now we have y hat times our 1 over x squared plus a squared hat equals 1 over x squared plus b squared hat. And we are actually given, originally from the beginning, what this Fourier transform is. So we have pi over b e to the minus absolute value of k times b. And likewise, we thus know the same transform for this. We just plug in a instead of b. And of course, we don't know what y is, so we just leave it as y prime, or y hat. So simplifying our terms, we know that our Fourier transform of y is going to be in this form, where we have a over b. So are we close to being done? We're actually pretty close. And so since our remaining term, e to the minus absolute value of k times b minus a, looks similar to our other Fourier transforms, then we expect our function y to be in the form of 1 over x squared plus b minus a squared, where we put b minus a into our coefficient up here. Of course, it's going to be multiplied by some type of scalar c, which we don't know, but if we match up the two sides, where we can basically make sure that they cancel out, I mean, we have a pi ba over here, but we want it to be times a over b. So, we just basically multiply everything over to the left side. And thus we find that this is our constant over here on the left side. So this becomes our constant c. And thus our function y just becomes the product of these constants over here times 1 over x squared plus b minus a squared. Alright, so that was part 1 of easy problems. Starting our second last easy problem, we're given this function that normally requires some contour integration. For this problem, we're not worried about the actual entire step itself, but we want to find the values of the residues at all the poles of this function. So we have cosine of the square root of z over z times the sine of z. Obviously, we're going to have poles where the function is not analytic. So, and the easy way to point that out is when the denominator is going to be 0. So how many points does that apply to? We'll find out. Okay, so then trying to find the values, the complex values that satisfy that the denominator is 0, we express our complex value z in terms of its Cartesian coordinates, x plus yi. So obviously for the pole z equals 0, because we had just a z in the denominator, x is 0, y is 0. That one's pretty easy. For the other one, sine of z is equal to 0. that one we have to be a little more careful about. Again, since we can take complex values, the sine function is actually not bounded between minus 1 and 1. It's actually bounded between, or it goes from negative infinity to infinity. So using our old trig formulas, you bring it up into our complex sine and cosine formulae. If you take the cosine of yi, it is also known as the cosh of y, or basically, if you want to look those up, go ahead. And then likewise, sine of yi is I sinh y. And of course, we need these two sums to still add up to 0. So, obviously we want somehow for both of these parts to cancel out or to equal 0. So what if option 1 is we let cosine of x equals 0? So we know that these would always be 0, which is good because we don't want any imaginary parts. But then we know that sine of x is either going to be plus or minus 1. And cosh of y is actually always positive. Yeah, cosh is always positive, so that's not going to equal 0 ever. So that's not going to work. That one's not going to work. Bye-bye. Other option we have is if we force sinh of y to equal to 0. And that only happens at one point, at the point y equals 0. Otherwise, it'll go from negative infinity to infinity as well. So then if sinh of y is 0, then it doesn't matter what cosine of x is. And then what we mentioned earlier, cosh of y is always positive. So then sine of x has to be 0. So we know that x then has to be some multiple of pi, where n is just, some number in the natural numbers. And thus, looking at it, on the complex plane, like we said, we have a pole at 0 from just our z in the denominator, and we also have zeros at every n pi from our sine function. The only other cause of concern is that we have two poles at 0, since, like we mentioned here, you could have 0 again as a pole. So we have a double pole at 0 and single poles everywhere else. So let's find the residues of those. So let's find the residues of the single poles first, because those will be the easier ones. In order to find the residues at the single poles, we take our function, our original function, we multiply it times x minus wherever that pole is. So in this case, just generically n pi. And then we have to take the limit as x approaches that point, because obviously, it's not going to exist at that point n pi, since we had 0 in the denominator earlier. So, plugging this into our function, we need to take the limit as x approaches n pi. And so we're going to have x minus n pi over sine of x. And fortunately for us, this limit of this quotient is going to equal 1. You can either check it with a L'Hopital rule, or just remember if you look at a function of x over sine of x, then yeah, it'll be 1. So we know that this part's going to go to 1, so then all we have left with is cosine of x over x, and then take the limit as x goes to n pi, so then our residue is just the cosine of root n pi over n pi. To find the residue at our 0 point, we could try doing the formula where we take the double root, we multiply it twice, we take the derivative, divide by 1 factorial, but instead I'm going to just try and force it out using a Laurent series. Basically, for our cosine and sine functions, we use our Taylor polynomial representations. Fortunately, we only need to take the first few terms, to get a really good estimate, especially since we're taking it around z equals 0, or x equals 0. I keep mixing x's and z's here, sorry about that. But, so we know that obviously for x really close to 0, this will be 1, this will be almost 0. So, we expand our terms out. We can factor out a z from the sine function here. So I factored that out here, and I only kept the first two terms of the cosine of root z function. Over here, I just regrouped all the other terms as j, and if you may remember from geometric series, if we have 1 over 1 minus j, it's 1 plus j squared plus j cubed, etc. Obviously only for values of where j is less than 1, and since we're taking this around z is 0, all of these sums together are going to be very, very close to 0, so less than 1, so we're fine. So that's how our j sequence pops up here on top. But since these all have z squared, z cubed, or z to the, that's wrong too. It should be z to the fourth. But since we have all these z squared, z to the fourth terms, we don't care about them too much. To find the residue, we only need to look at the first couple of terms of this Laurent series. So down here, basically we can ignore all these things. So what we have left is 1 over z squared minus 1/2 times 1 over z. And if you may remember, the residue is the coefficient in front of the 1 over z term. So thus our residue is just minus 1/2. Alright, so starting next week I'm going to be doing more complicated problems. This is Big Man saying later.